We will in this lecture discuss a topic which is important across all the determining algorithms we discussed previously, be it clustering, regression, classification. The talks here that we will talk about is dimensionality reduction. That means, you have a number of attributes in your data, often a large number of attributes, but the question is often all these attributes are not really required or important for the determining tasks. So, what we do in dimensionality reduction is to reduce the number of attributes that we actually need. So, for example, suppose I have a table, a data table like this. Say a credit card fraud detection data table. And we want to decide on the classification problem whether fraud or not fraud. Not fraud. Okay. And maybe there are a lot of attributes, maybe income, age, okay, maybe many other attributes. So, suppose I decide that I do not take all of them, I take only few of the attributes, then I am in effect doing a dimensionality reduction. Why it is dimensionality reduction? Because each of the data points, each row in this table, you can consider as a point in some space as a vector, and the number of attributes you have is the dimension of that vector, dimension of that point. So, what we are doing in dimensionality reduction is to reduce that dimension, and this is done for the following purposes. First thing is that it removes something called curse of dimensionality. That means, as your dimensions increase, as you need more and more attributes in your data, you need more and more training samples to train your algorithms. More you increase the dimension, more you need training samples. So, naturally in the previous discussions it was evident that it is dependent on the. So, this problem is the curse of dimensionality. It is more the dimensionality, more training set, and it grows exponentially. That means, if the dimensionality goes up by 1, you need square of the number of training sets that you need, it goes up rapidly. Okay. So, that is the first motivation. Second motivation, of course, if you increase dimensionality, your computation time will increase, your storage will increase. Okay. So, you want to reduce dimensionality to improve upon computation time and storage. That is the second motivation. The third motivation is that you can more the dimension, more difficult it is to interpret the data, to visualize the data. Okay. So, we human beings cannot visualize beyond 2 or 3 dimension, and also this dimensionality reduction will help us to eliminate the noisy features, the features which are not relevant, okay, noisy features. So, in this lecture we will discuss some of the techniques for dimensionality reduction, but let me first explain you what it actually means. There are two types of techniques. One is known as attribute selection, or feature selection. What we do in this approach? Let me take an example. Suppose I have two attributes and maybe my data points look like this. So, in my attribute selection, I have to choose one out of these two features. So, I have to choose an attribute subset. So, if my original set of attributes are x 1 and x 2, I have to choose either x 1 or x 2 is the subset. So, this attribute selection actually means attribute subset selection. Okay. So, in case of 3 attributes, if I had 3 attributes, I could have chosen only x 1, x 2, or I could have chosen x 1 and x 3, or I could have chosen x 2 and x 3, if I had to choose 2 out of 3. Okay. So, what does this choosing means? See, for example, in this case, so out of x 1, x 2, if I choose only x 1, it actually means projecting each and every point looking at their x 1 coordinates only. So, basically it means that projecting x 1, x 2 plane points to x 1 or x 2. Similarly, in this case if there are 3 things, x 3, if I choose 2, it is a projection of a 3 dimensional point either to this plane or this plane. Okay. So, attribute selection is equivalent to projection, but which of these two projection you will take? You look at the projection. If your objective is to classify the examples into these two classes, then maybe the x projection is better. X projection is bigger, because if we project x 1 projection is bigger, because if we project to x 2, everything gets mapped to this set of points. So, I can write than x 2. Okay. So, this projection has more separated classes than this projection. So, naturally x 1 is a better choice. This principle is generalized in attribute selection algorithm. How is generalized? It is generalized in the following way. So, every projection that we get, every subset that we get, you can evaluate it, you can give it a score in terms of class separation or any other criteria. Okay. So, for example, here it is better than this. Okay. This projection is better than this projection. So, this I have to define something called attribute subset evaluation index. Okay, which may take a form of a class separability. And then what we do? Find the subset that has the best evaluation index. Okay. So, in this case there are two subsets only, x 1 and x 2. In general, if we have say x 1, x 2 up to x d, how many subsets are possible? 2 to the power d different subsets are possible. Okay. If we have originally d features, capital D features, 2 to the power d different subsets are possible, d minus 1 actually. So, each of these subsets I find a evaluation index, class separability, and choose the best. So, this is a optimization or a search problem to find the best subset. Okay. So, what I will quickly do is to discuss one evaluation index and few search optimization or search techniques. You want to find how much separated two classes are. If we know the probability distribution of the first class, let me call it P 1 x, and the probability distribution of the second class P 2 x, I can define a measure called Bussons. This is one particular form of KL divergence. Okay. So, what you do? At every training point, you find out how much probability class 1 gives, how much probability class 2 gives. Take their likelihood ratio. So, this quantity is ratio, multiply it by their probabilities, add up over all the training point. So, this projection, if we consider x to be this x 1, we will have a higher KLD than this projection. Okay. There are other measures also, I am just giving an example. You have so many subsets. Do not that for every subset you have to find KL divergence. Or any other evaluation measure, need not be KLD. This is not feasible. Okay, too many computation. So, there is another method greedy method. Okay, so x 1 you keep, you add x 2, you add x 3 and so on, and select which is the best. Kerr divergence again. Select it. Okay. So, this is a greedy method, not optimal, but often it works. The opposite of this is okay. So, there you take all the features and remove the best, remove the worst, again remove 2, keep the rest, remove 2. Okay. So, the reverse of this. Okay. So, these are the two methods. There are other methods like beam search, sequential floating forward search, branch and bound search, which are used. So, this is a very important step. This is a very time consuming, but important step. There are different ways of doing this. Okay. So, wait, I will come back to this. Okay. So, this is what I have told. You have to select. So, these are the approaches, brute force. There are again two approaches. If the evaluation measure is tuned to the data mining algorithm, it is called a filter, embedded. It is not, it is called a filter. Okay. Filter and wrapper, two approaches. If you use the data mining algorithm, it is wrapper. If you do not use it, it is called a filter. Sometimes the algorithm itself does the embedded dimensionality reduction. Okay. So, this is the technique, this is feature selection. In our next talk, we will discuss another group of algorithms called feature extraction algorithms, okay, in our next talk. So, thank you for this talk.